You see the screen, please? Perfect, thank you. Okay, before I'm starting, to continue in the transistor or the BJTs, to remind you about Friday morning, 8:30, test 1 in B2 to 51, 8:30. The test has the same format as the ELE105 Part A long type questions, around 3 questions, 3 problems. The multiple choice questions, 30%, 10 multiple choice questions. The material that it's covered for test 1, it's up to the Zener diode, means that we covered the semiconductors, we covered the diodes, the application of diodes as a rectifier, the half-wave rectifier, full-wave rectifier, using a CT or the center tap transformer using just 2 diodes, and the full bridge rectifier. Any questions that you may have about the upcoming test? Any questions or any clarifications that you require for the upcoming test? Everybody is okay with that? Okay, let's move on the BJT. First of all, how we can define the BJT? It's a 3 terminals, means that has 3 semiconductors and actually 2 junctions between the base emitter and the base collector. Means that the basic functionality or the operating regions of the BJT, it's actually limited by the 5 limits, but has just 3 operating regions. On the left side, and this is what I introduced previous lecture, on the left side, if I'll draw it, in this way, we have, the saturation, and we'll define what means saturation. On the lower side, we have the cutoff, and the middle region, which is the most applications for the transistor, is the active region or the linear region. What means linear or active region? Linear gives you an idea about the functionality of a transistor when it's used as an amplifier for a given base current. You notice that I'm having actually a family of collector curves based on the base current. You notice that this active region, which is in the white color, has the 5 limits. Again, we'll come back and describe the 5 limits of the active region or the linear region. At this point, we have to define what means or what are the conditions to place the transistor in saturation, the cutoff, and the middle point or the center area of the graph. You notice that on the y-axis is the IC, usually it's given in milliamps, and on the x-axis is the VCE or the collector emitter voltage. Remember the notation, C is for the collector, means that all the components or the characteristics or the parameters related to the collector, it's has the index of C. All the parameters that are related with the base current, base voltage, and so on are related with B. VCE, it's the voltage between the collector and the emitter. That's why it's using, double subscript to emphasize that the voltage is between the base and the emitter. To remind you that if we would like to place the transistor in the active region, we have to make sure that we have the two conditions met. One is in terms of the base emitter junction, which has to be in forward biased, and the base collector voltage or diode that has to be in reverse biased. Now, first of all, we'll take one of the three regions to define or how to calculate actually the parameters for the saturation region. We'll define saturation, we'll define the cutoff, and after that we'll focus on the linear or the active region. I mentioned that most of the time is not given just a single characteristic, means that we have a group or a family of the collector curves which depends on the base current. We mentioned that the relationship between the base current, the IB, and the IC, the collector current, is through the gain factor, or it's the gain for a DC type voltage applied to it. Another symbol or another notation that it's used for the beta DC is the HFE. We'll discuss a bit later, and I'll show you in diagrams, in the specs of a transistor where we can find this beta DC or HFE. Now, that's an example. Suppose that the characteristics or the curves or the specs of a transistor is given. And suppose that we are trying, to use the transistor for a base current of 30 microamps. From the graph, if we are placing, the graph, at this point, we notice that we have the two coordinates. Those two coordinates, actually the IC and the VCE, it will make the Q point. You remember that I introduced the Q point or the operating point in the diodes, because I'm using, intensively in the BJTs in the transistor. This actually, this point or the Q point of a transistor is defined by the applied voltage and the external devices, external components, actually the external resistors that are placed around the transistor. Remember that the transistor, the way that is given as a semiconductor, it doesn't work. We have to place it in a circuit and make it work as a transistor as an amplifier, or in the active or linear region, or as a switching transistor. And that's why we'll discuss a bit later about the transistor in switching mode, or switching region between the cutoff and the saturation region. Now, you notice that, and that's, the example that I may suppose that I have, these characteristics or this family of the characteristics for a transistor. And we can see that, for a given or for a choose base current, in this example, I choose the 30 microamps. The projection of the current on the y-axis is the IC, means that probably, at this point to have the 5 milliamps, and knowing the base current as 30 microamps, we can determine what is the beta DC. Most of the time, the beta DC is given, means that we have to find the IB, we have to find the IC, and knowing the beta, or given the beta of the transistor, knowing the IC, we can determine IB, or reverse way. Knowing the IB and the beta DC, we can determine what is the IC. That's, let's say, the basic application of the characteristics, or the characteristics that are given or are provided by a manufacturer in order to determine the beta from a graph, or from a provided graph by the manufacturer. Now, the first region, and remember that on the left side of the IC, or the y-axis, we have the saturation region. Now, let's try what means saturation. Now, let's take the approach from day-by-day use. I may give some hints about the saturation. Suppose that at home we are using a sponge, and when we are saying that the sponge is fully saturated, when you are saying that fully saturated, what that means? The sponge cannot absorb more water, means that it's saturated. Another application of the terminology of saturation. Suppose that we are making in chemistry a saturated salted solution. What that means? The water cannot dissolve more salt in it, means that the solution is saturated. In the same way, we can look for saturation in terms of the maximum current on the collector of the transistor. Means that we are looking in the transistor, in the circuit of a transistor that it's placed, and in this circuit you notice that I'm having this closed loop. Okay. Now the question is how we can determine what is the maximum current in the collector of the transistor. Now we have to make the assumption that the collector emitter voltage, or the VC, means that the collector is more positive than the emitter. If this voltage is almost zero, and that's why I put in as an example here, the approximation is 0.2 volts. Another consideration that we have to make into designing or making the calculations for electronics. Most of the time we are dealing with very large quantities like 10 volts, 20 volts, 40 volts, 100 volts, and so on, as the VC, or the voltage, the collector voltage, or the emitter current, and so on. And the other quantities can be very small, like in this example, the VCE is very small, 0.2 volts, but we are comparing the 0.2 volts with 10, 20, 50, or 100 volts VCC. You notice that is given as a double subscript in order to avoid the confusion between VC. If you remember, we discussed about that's the VC, or the voltage at the collector with respect to ground, and VCC as the voltage source. Means that the annotations in terms of the voltage sources is double subscript. VCC is the voltage applied to the collector, or the voltage that is supplied to the circuit. Simply VC or VE means that the potential at the collector, or the potential at the emitter, or the VB it's another notation for the voltage or the potential at the base with respect to ground. If the maximum current is flowing through this output loop, that's why I may have, two different loops, and we'll go back in solving, the circuits, and I'll show you one more time, the two loops. That's, the input loop, and we're applying, KVL on the input loop, and that's, the output loop or the collector loop that has a series of the supplied voltage, the RC as the resistance connected in series with the collector. We may see another circuit that has, a resistor in the emitter. Means that I'm still applying, the KVL in the output loop or in the emitter collector loop, and another loop that is actually created for the base or as the input loop. Now the maximum current, and I will clean up a little bit, just to have a nice clean, diagram. Now we are looking to find what is the maximum current or the saturation current. You notice that this saturation current is given or is imposed by the resistor in the collector and the supplied voltage. We are making the assumption again that voltage VC on the saturation is very small, or actually is equal to 0 in our calculation, even if we know that this collector emitter voltage is very small, like 0.2, 0.1 volts. In electronics, if a quantity is at least 10 times smaller than the other quantity, may be neglected. Remember that we are doing the same approximation when you are calculating the emitter current and the collector current. But at this point, you notice that this voltage, the VCE, the collector emitter voltage at saturation, is very small. Going back to this diagram, you notice that the collector emitter voltage, VCE, at saturation is very small. Again, practically, this voltage is it's close to 0 or 0.1, 0.2 volts, means that we can neglect, this collector emitter voltage or saturation voltage, or we can make, the assumption that, the collector emitter voltage at saturation is equal to 0. Means that we can determine what is the maximum current that flows through the transistor when a voltage VCC is applied to the circuit and is actually limited by the resistance RC. Again, applying the KVL in the output loop, we determine that the VCC minus the drop voltage across the collector resistance is equal with the VCE. Again, we are making the assumption that the VCE is equal to 0, means that to determine the IC or the IC max, which is the saturation current, is the VCC divided by resistance RC. That's one of the easiest way to determine or to calculate what is the maximum saturation current or the maximum current that can flow through the resistor if it is placed in a circuit for a given RC, for a given VCC. You notice that when the transistor is in saturation mode, the relationship between the collector current and the base current through the beta or the gain or the beta DC is not longer valid. Means that this diagram, if I'm increasing the base current above, the saturation current, or in this diagram, you notice that saturation current is 25. And suppose that I'm increasing the base current to 100 microamps. 100 microamps, it will not increase the collector current. That's why it's called saturation. Even if I'm going, way above, like 120 to 100 microamps, still the maximum current that can flow through the transistor is limited by the resistance RC and the supplied voltage, and that's the maximum current that can flow through the circuit. Now on the cutoff, now going back to the diagram, this diagram or the other diagram, you notice that in cutoff, or the IB is equal to 0 amps, or there is no current applied on the base of the transistor. Now the question is, what is the collector current when there is no current applied to the base? And you notice that there is a small amount of current. Usually it's, the leakage current between the collector and the emitter. This leakage current is in terms of micro or nano amps, means that we can neglect, we can ignore, this current, and we can make, the collector current in the cutoff as the 0 amps. Means that on saturation, transistor is fully open, or the transistor is in on state. When the transistor is in cutoff, is in off state. Means that we can use, the two regions, the saturation and the cutoff, to place or to use the transistor as a switch from the fully saturated into a cutoff or the off state of the transistor. What we can calculate, for this for the same diagram. Again, I'm applying, the KVL in this output loop or the collector loop. You notice that if there is no base current, or the IB is 0, or there is no voltage, no current applied on the base, the collector current is equal to 0. Now, if the collector current is 0, question is, what is the drop voltage across the RC, across the resistor in the collector? Means that the voltage across the resistance RC is 0, means that the VCE, it's the same or it's equal with the VCC. Again, why? Because there is no base current. If there is no current applied on the base, the IC or the collector current is equal to 0. If there is no collector current, the voltage drop across RC is equal to 0, means that the VCE in the cutoff is equal, or it's, you notice that is the approximation, or it's equal with the VCC. Remember that we discussed about, the open circuit and the closed circuit. That's, or the transistor, it will act as an open switch, or is an off state. The cutoff region or the off state of the transistor. That's, the VCC, which is equal with the VCE in the cutoff. Going back to the diagram, you notice that I'm having the VC max. The VC max is actually equal with the supplied voltage VCC, and we determine that the current, that the IC current, which is equal to 0 in the cutoff region. Again, there is no base current. The if there is no base current, you notice that the base emitter and the base emitter junction are in reverse bias. You notice that there is no current, and remember that in order to place or to have the transistor in the active region, the two conditions must be met. The base emitter has to be in forward bias and the base collector junction has to be in reverse bias. Um, in this condition, or if the base current is equal to 0, both junctions are in reverse bias. And the transistor is in off state, or it will act as an open switch, or there is no current that flows through the transistor, or the IC equals to 0. I put them together up to this point, the equations that we may use in this course. And those are the equations that are given for the test 2. The VBE must be equal or greater than 0.7 volts. IC is equal to the beta IB. Or, from this equation, I can determine the beta as the IC over B. Or finding the relationship between the emitter current and the collector current. Now, I'm substituting, the beta or the IC with the beta IB and applying, the KCL, the current that is on the emitter. We may rewrite this equation as the emitter current as the IB plus the IC. Substituting IC with the beta IB will end up with beta plus 1. But remember that beta is a very large number, like 50, 100, 400, 500, and so on. Means that beta plus 1 will not make a big difference in using this equation. And that's why we can make, the approximation in our calculations that the IE is equal, or it's almost the same as the IC. The difference between the IC and IE has the IB in it, but that, that's a small amount of current that is added on top of the IC. Means that if the IC is in terms of milliamps, like 5, 10, 100, 400 milliamps, the IB is in microamps. Again, that's, the approximation, and this is, the rule that most of the time, I'm not saying always, but most of the time is applied. If a quantity is at least 10 times less than the other quantity, that quantity can be neglected. It means that the IB is at least 10 times less than the IC. Means that we can neglect, the beta plus 1 or the IB from this equation. And I put that in right, the KCL for a transistor, the emitter current is the sum of the two currents. But again, we can neglect, the IB because the value or the amount of the base current is much smaller than the IC. And that's why we can make, the approximation between the IE as being equal with the IC. Now we have to make, the load line. I mentioned that a transistor, when it's placed in the circuit, knowing the IB, knowing the load line, we can determine the behavior of the transistor, how it will work in the AC applications. Now, the load line has the two limits. Actually, the intersection or the intercept with the y-axis, which is given by the saturation current, and the intercept with the x-axis, which is the cut-off region. And we just determine that if there is no collector current, the maximum collector emitter voltage is given or it's equal with the VCC, and that's the approximation that we can make. Making the connection between the two points. One is the saturation current, and the other one, the VCC. We are placing the transistor in this active region on the load line. Means that we are looking actually to use the middle point or the middle region. This is what we are looking always to place the transistor in the middle region. If the transistor is placed close to the saturation or close to the cutoff, the input signal will be limited. Means that I'm having just a small amount of voltage or a small amount of current that can be applied on any of those two extreme areas, or close to the saturation or close to the cutoff. Means that there are limitations in the applied current on the base if the transistor is close to the saturation region or close to the cutoff region. The best practice, and keep in mind that the best cue point, most of the time I mentioned that the midway between the saturation and the cutoff. What that means that a small change or applying a large range for the input or the base current can be applied on the transistor if the cue point is somewhere in the mid range or the mid point between the two extreme values. Remember that on this simple circuit, and this is most of the time that we are seeing, the saturation current is given by the voltage source, and the external RC or the collector resistor on the other extreme point is the VCC, which is the same thing with the collector emitter maximum voltage, which is limited by the supplied voltage on the circuit. Now, again, for this circuit that we discussed, that's the basic circuit that has just two resistors. Remember that the RB is the resistance connected on the base, the RC, the resistor connected to the collector of the transistor. The two limits, the VC saturation or the VC max, it's the VCC divided by resistance RC. Again, making the approximation that the collector emitter voltage in saturation is equal to 0. And on the opposite side of the load line, we have the VCE, which is actually limited by the supplied voltage, the VCC. The saturation current, and I mentioned that you may see an abbreviation as the ISAT, like saturation current, or sometimes is the IC SAT, or the collector saturation current. Means that we may see both notations for the saturation current in the specs, and by the end of this lecture I will show you the specs of few transistors, and actually what we are looking for and what we have to take into consideration when you are choosing a transistor. Now, to calculate, and that's a practical example, to calculate the saturation current in this circuit, I mentioned that that's the example that we are using the 0.2 volts, but I'm just showing that it will not make a big difference in our calculations. Means that I can neglect that 0.2 volts, and you are taking just the VC over the RC. Now, if you are taking 15 volts, you notice that 0.2, it's much smaller than 15 volts. Divided by 3.3, that's 4.48 milliamps. If I'm neglecting, that 0.2 volts, you not make, a big difference in the calculations. If the transistor is saturated, actually, what do we have to do? We have to compare, the saturation current with the operating current. Remember that. That's the maximum current. We don't want to have or to place the transistor closer to this saturation current. Now, how we can determine if the transistor or the actual value of the collector current is closer or it's placed in the midway between the two extreme points, the maximum current and the VCC. Now let's have a look on how we can calculate the IB. The IB in this diagram, you notice that I'm having an external source that is connected through the RB to supply a current on the base. How we can calculate this current? Again, I'm applying the KVL on this input loop or the base loop, which is the 3 volts minus the drop voltage between the base and the emitter. Again, why do I have to take, that 0.7 volts from where it's coming? Remember the two conditions that I have to met, to place the transistor in the active or linear region. The base emitter must be in forward bias, means that the voltage between the base and the emitter for a transistor like that, it's 0.7 because it's in forward bias. And the supplied voltage 3 volts divided by the resistance, notice that it's a large resistance because the IB has to be a very small value and gives, excuse me, gives, a very small current as the IB, like, 10.45. You notice that is in microamps, means that going back to the basic definition of a transistor, it's a current control device, means that I can adjust this small current to control actually 2 milliamps, which is the current on the collector, and we made the assumption that the two currents are the same or are equal, means that the collector current is the same or is equally the emitter current because the IB is a very small current. Now, knowing the beta of the transistor as 200, knowing the IB, we can determine what is the collector current. Collector current is 2.09 milliamps, but the maximum current is 4.48 milliamps, means that we are placing this transistor closer to the closer to the mid range, of the load line, and this is what we are looking, most of the time when we are designing a circuit, when we are looking, to place the transistor on the load line, choosing, the midpoint. And this is, how we can evaluate, how we can determine if the Q point or the collector current for a specific voltage collector emitter is, the midway or, in the middle area of the load line. On the data sheet, and I mentioned that HFE, it's almost, or it's the same symbol as the beta, or simply, beta DC. Okay, means that I may see, the HFE or the beta DC having, the same meaning. In the same time, and I mentioned that in some vendors, we may see the minimum, we may see the maximum, or sometimes we may see a typical value. And that's why I will show you a bit later, the specs from different companies for some other transistors. But this is, what we are using in lab, and this is what we use before, 2N3904. You notice that the transistors, and I mentioned that diodes most of the time are labeled as 1N. The BJTs or transistors are labeled, or the first two symbols, it's the 2N. 2N, most of the time, it's a transistor, that's a BJT. And we may see the equivalent PNP transistor as 3906. That's an NPN, and in specs, in data sheets, for different from different vendors, it will specify what is the complementary transistor for an NPN and or the PNP. Now you notice that the gain in DC, or the gain in current, it's a maximum of 300, and the minimum that is guaranteed by the vector is 100. In calculations, we have the two, the mean and the max. I will choose in calculations, in designing, the lowest value, just to make sure that I'll end up with a close value to the of the beta, closer to the minimum value. I will maintain the transistor into the operating point. Now, another or some other parameters that we have to take into account. Maximum voltage between the collector and the emitter. I put that in writing because most of the time we'll see the VCEO, means that the base is open, means that there is no current applied, or there is no voltage applied on the base. Collector and emitter, you notice that it's in this order, collector, emitter, with the base open, means that the first two letters, or the first two indexes, shows what it's connected to the circuit, and the O, it's for the base. We may see a combination between CE, CB, or the EB. Again, the third terminal, it's disconnected or is not connected to the circuit, or is an open terminal. The other parameter that we may look and we may interested is the voltage between the collector and the base with an emitter open, means that that's the maximum reverse voltage that can be applied between the base and the collector. The other voltage is between the emitter and the base. You notice that is not the base emitter, and we discussed that has to be 4 bias, and usually it's 0.7 and so on. That's the reverse bias. That's the reverse bias between the base and the emitter. That's why it's given as the VEB, not the BE, with the collector open. Collector current, this is what we are looking for to maintain, or to make sure that in our calculations we are designing the circuit with an IC in the Q point less than the maximum collector current. Maximum dissipation, I mentioned that we may see beta or beta DC as the HFE. That's for emitter in specs. That's another way of defining the beta DC. Now, in order to make the distinction or the difference between DC and the AC quantities, remember we discussed in ELE105 and 205, all the AC quantities are given with a lower subscript. And remember that we may see the RE. You notice that R is a lower case and E as a lowercase, means that the resistance for the AC quantities are labeled with a lowercase for the AC analysis. In DC analysis, all these quantities are uppercase, and that's the example VCE, uppercase V, uppercase C, and E, means that everything in uppercase is related to the DC quantities or the static condition or the um, DC conditions of the circuit. In the AC, we may see the voltage between the collector and emitter, but you notice that the collector and emitter are given as lowercase, sometimes italic, means that all these quantities are related with the collector emitter with the AC quantities. We may see another notation, and remember that RC, uppercase R, uppercase C, is for the resistance in the collector, but in the same time we may see a lowercase c as the resistance in the when the transistor is in AC mode or the AC analysis. To show you some of the specs for 2N3904. That's an ST, that's the logo for different companies, and we may see ST, we may see Motorola, we may see Fairchild, we may see different logos or different companies. For example, ST is the ST Microelectronics, which is one of the biggest electronic devices companies in the world. It's actually a Switzerland, or it's a Swiss company, but they have, it's like a multinational company. It's not only in, but it's based on the European market. And we may see the two main types. It shows you the case. We may see straight legs or widened legs. The 1, 2, and 3 are given in the schematic diagram, means that 1 is the emitter, 2 is the base, and 3 is the collector. For example, they may put, the complementary transistor, means that identical transistor, except that is an PNP. That's an NPN transistor that we are using in lab. That's, the 2N3904, the equivalent transistor, but as a PNP is 3906. That's why they call complementary transistor as 3906. That's a PNP, NPN, and you notice that the symbol is for an NPN transistor. We mentioned that that's the VCB with the emitter not connected, or IE equals 0, or is open emitter. That's the maximum value for the base collector, the collector base. I said that the IC is given as a typical value as 200 milliamps. The P total, that's the maximum power dissipation. That's the one of the important information that we are looking for, or the parameters, and that's 625. That's in milliwatts. What else we are using? I said that that's the ambient, that's the case. Um, collector voltage. Ah, okay. Now let's have a look on these detailed specs. We have the minimum, we have the maximum, and we have the typical in the middle. Not always is given the minimum, typical, and the maximum. Sometimes gives you the maximum current. Means that we have to take the this current in our calculations. But again, I'm not using the cutoff current. We are using the I mentioned that that's the gain current, DC gain current, and is specified for a different collector emitter voltage and a different collector current. You notice that for different voltages and for a specific voltage and different currents, we may have a range of the beta, but usually maximum is 300. You notice that there is a restriction in the maximum bandwidth. We'll discuss a bit later when we'll talk about the transistor as a switch, the TD and the TR, the delay time and the rise time. And you notice that that's the two values in nanoseconds, that it will limit actually the maximum frequency of the transistor in circuits. Technical data, that's the physical dimensions. Okay, just one more thing, because I highlight, that's an American company, that's for a similar transistor, but you notice that gives the specs and in a different order, and the terminals in a different way than the other specs. That's why it's not standardized. Now I highlight, what we are looking for. Collector emitter, the IC, the maximum current 200 milliamps, and the PD, the total power dissipation. Again, it's given at the ambient temperature at 25 degrees. If is, remember we talk about, derated value, that's 5 milliwatts per degrees Celsius. That we have to take into account. Collector emitter breakdown voltage, that's not very critical in our calculations, but that's important to know exactly what is the maximum voltage that can be applied between the collector and the meter. The collector and the base current, that's in nanoamps, and the gain, again, it's specified for collector emitter voltage, and the IC current typically is 150, and this is what I will take into account in our calculations. You notice that the collector emitter saturation, I mentioned that it's around 0.2 value. That's the typical value for the collector emitter saturation voltage. That's for the small signal, which is the AC analysis. You notice that the AC gain can be a bit lower than the DC gain. That's why we have to take into account, what is the gain or what is the current gain for the AC or the small signal. We are not going to details about the small signal analysis, but I will give some ideas about the AC analysis, which is more complex than the DC analysis. Any questions, comments, concerns, please? If you don't have any questions, have a nice day. See you on Friday.